Hi folks, in this video I'm going to show you how to perform a bivariate regression using JASP. First open up JASP. Once JASP is open, go to Show Main Menu, Open, Data Library, and Regression. Go ahead and select Physical Activity in BMI since JASP indicates that this demonstrates use of linear regression. When the file opens, become familiar with the data set. You can see that PA represents the physical activity indicated by average daily number of steps in thousands of steps per day, and BMI is the person's body mass index, and this is determined by taking a person's weight measured in kilograms and dividing it by the person's height in meters squared. To perform the regression, go to the top where it says Regression and choose Linear Regression. Under Linear Regression, we're going to take our criterion or Y variable of interest, which is BMI in this case, and move it to the dependent variables box, and then take physical activity, which is the steps or predictor variable in this case, and we're going to move this to the covariates box. If we scroll to the bottom, a couple other things that we can make sure that we checked. For example, the model is all set. The statistics that we want to run, we can get descriptive statistics, part and partial correlations, and we can get R-squared change values. We can do this at the 95% confidence interval, and we can go ahead and select those outputs. And when we take a look at these data, we can get the information to determine if the line of best fit is a good line at estimating an unknown BMI of interest or Y value compared to the Y mean. And so if we take a model that assumes the null hypothesis, or HO, it assumes that the R is going to explain no correlation at all. And so that's why you have all of this missing value. But the alternate hypothesis, which is testing the line of best fit, we look at the p-value. The p-value, which is being used to test the F statistic, or the F change in this case, and that is testing the R and R squared values. And so when we look at the model summary, this is telling us if the line of best fit, Y predicted equals A plus BX, if that line is statistically a better line at estimating or predicting the value of BMI, our criterion variable, our Y variable of interest, than the Y average, the average for BMI. And in this case, it says that the p-value is statistically significant or is better at predicting that value. Now, if we scroll down and verify these data with our ANOVA, remember the ANOVA is what's going to tell us if the line of best fit itself is a better line at estimating the unknown Y value of interest compared to the Y mean. And so we're going to look at the p-value for the F statistic, and you can see that the p-value, similar to the model summary, is statistically significant to the same extent. Because really they're showing the same thing, right? 0.001 and 0.001 are the same values. 17.096 is the same value here. So in both these cases, you can determine whether the line of best fit, the regression line, the Y predicted equals A plus BX equation, if that's a better equation to estimate the value of a BMI than the Y mean. In this case, we see that the line is in fact better at predicting that. How do we know? We use ANOVA, sum of squares between, or explained variance, which is the regression, divided by its residuals, or the sum of squares that's unexplained. And so to determine it, you take the sum of squares total, divided by n minus 1, so two variables, an x and a y, minus one predictor, gives us a mean square of 228.377. And for the residuals, it's n minus k minus 1. And so you take the total sample size, minus k, one predictor, minus one restriction, gives us 98. And so if you were to do that and take 1309.101 divided by its degrees of freedom of 98, you would get 13.358. If you took explained over unexplained by taking the 228.377 for the between and divided it by the 13.358 for the unexplained or the within, you would get an F statistic of 17.096, which is the F observed value. You would then take that F observed value and compare it to the F critical value that we determined in previous videos. And if the F observed value exceeded the F critical value, it would tell us that the line is a better line estimating the Y mean compared to the Y mean itself. So this tells us whether the line is significant, but sort of a post hoc option for this would be the coefficients box. And so one of the things that we need to do then is to determine if the predictor is significant at estimating the unknown Y predicted value itself. And so what we're going to be exploring here is the p-value for the t statistic for the unstandardized B slope. And so it's called the P for the T for the B. The P value is testing the T statistic, and the T statistic here is testing whether the physical activity predictor, that slope, if that is a significant predictor at estimating the unknown Y value of BMI. And in this case, the P value is smaller than 0.05 and it's statistically significant. And so when we take a look at the P value, we see it's smaller than 0.05, which tells us that the T test that's assessing that slope for physical activity step counts is a significant predictor, and we can effectively estimate body mass index from a person's physical activity habits. So in this case, what would the Y predicted equals A plus BX equation look like? Well, the unstandardized 29.578, that's going to represent the Y-intercept. So that's your A plus negative 0.655x. So your line of best fit would be negative 0.655 times the person's physical activity value, and then you would add 29.578, and you would estimate within a reasonable 95% confident range what the person's true BMI would be. Now, interestingly, in a bivariate regression, when you look at the standardized slope, so if you were to standardize this B into a beta, right, using the sample form into the standardized form, you would see that the negative 0.385 matches the 0.385 that we see here for the R, the Pearson's R correlation. And that's going to be the same because remember, beta and Pearson's product moment correlation coefficient in a bivariate or X predictor and Y criterion 2 variable scenario will be the same thing. And so how much of body mass index is explained by physical activity counts? Well, you take the R value and multiply it by itself. And so if you took 0.385 times 0.385, you would get 0.149. So about 14.9% of a person's body mass index can be accounted for by the amount of physical activity that they step in thousands of steps per day. But similarly, the amount of steps per day can be directly attributable to the person's BMI, and 14.9% of that is attributable to that. So it works both ways. So when we look at these data, you can see that in a bivariate regression, we can not only determine whether or not the line is significant compared to the wide average. Once you look at these coefficients box, it tells us if the predictors are significant at doing that. And in the case of a bivariate regression, it's going to be the same thing, right? If the line's significant, there's only one predictor, so the predictor is going to be significant. But when you start adding in multiple regression, where you have more than one predictor and one criterion variable of interest, you might find, for example, that the line is significant, but some predictors are significant at predicting that value, and other predictors are not significant at predicting that value. So it just helps us to provide a better understanding of how we generate linear regression. Now, the last thing to think about is part and partial correlations. So we taught you that there's a zero order, part, and semi-partial correlation. This is going to be the same value because we're still in the business of using a bivariate regression. But remember, when we have more than one predictor, as we do in multiple regression, it's completely possible that X predictor 1 and X predictor 2 are significantly collinear with each other. And so in those situations, it might make a lot of sense to go ahead and partial out the variability that is effectively shared between the predictors themselves and eliminate that variability because we're only interested in how much each of the predictors overlaps with the Y criterion itself. And so I hope this video was helpful, and we'll see you all in the next one.